कहने को तो ये हमारे यहाँ सब ऑडिटर है, लेकिन सच बात यह है कि बहुत कम दिनों में इन्होंने बड़ा मजबूत रिश्ता बना लिया हमारे अखबार से। अच्छा, तो आप अपनी कामयाबी में इन्हें हिस्सेदार मानते हैं? कहें तो कल ये खबर अखबार में छापो। क्या तुम हो रहे हो? इस पार्टी में तुम्हें दूध या गंगा जल तो मिलेगा नहीं और शराब की तासीर जमती नहीं।
क्लास है।
Good evening, everyone. So let's wait for a few more minutes. We have got somewhere around 31 participants. Maybe another 1-2 minutes so that we'll wait for some more people to join in for the day 2 session of our LTE fundamentals. Thank you so much. I hope I have shared my screen. I hope my screen is visible. If someone can acknowledge, be great.
Yes.
Yes, your screen is visible.
Thank you. Thank you. Okay, once again, yes.
Before
yesterday I had a silly question.
Yes.
A downlink. A downlink means BTS or eNodeB to mobile, right?
Yes. Always when we say downlink, it is from, let's say, I consider 4G as my base station, which is called as eNode B. So the downlink is always from the base station to the mobile. This is called as downlink, which we usually typically put it as DL. And the transmission which happens from the mobile end to the eNode B, this is called as uplink. So typically we call mobile as UV.
Okay. Actually, downlink and uplink, it is download respect to mobile actually. If it is download, then it is through the downlink.
Okay, basically almost it means change. It means interchangeably you can use that. Basically, download means you are downloading from the server, right? So server is nothing but is connected to eNode B itself.
Yes.
So download will always be again from eNode B itself. Upload will always be to this particular eNode B. So you can put it as upload or download. But typically in wireless communication, we call it as downlink and uplink.
Yes.
Okay, thank you so much. Any other doubts, or shall I continue with our discussion?
Yes.
Okay. So good evening once again. Let's start with our day 2 discussion on LTE fundamentals. Already you are aware about the objective. So basically yesterday we looked at more on the motivation or the evolutionary path towards 4G LTE. Basically we looked at something called, we have ITU, International Telecommunication Union, which gives standards on these technologies. So in that there was a bifurcation. There was one group which was called 3GPP. This is where we look at with respect to LTE. There is another group called 3GPP2. So basically this is North American, this is European standards, and this becomes a North American standards. So I can mention it here. So EU standards. And typically we looked at what are the different sort of generations we have, and each generations, what are the typical standards we have under these groups. So we follow more of 3GPP. So basically we looked at the 2G, which is GSM, GPRS, and edge architecture. And we also looked at WCDMA / HSPA architecture, and then we move towards LTE. So 3GPP2, we didn't look at any sort of architectural point of view, but we already know that they started with something called CDMA IS95, Interface Standard 95. Then they moved towards something called CDMA 2000, and then they got into something called data services, which is EVDO, Evolution of Data Optimized. So I hope you're all familiar with these sort of standards, what we have got, and all the full forms. Please let me know if you have any doubts regarding this. So I will try to revisit these things now, just a quick recap, and then I'll move towards the today's topic. Today we'll be largely focusing on the LTE air interface side. Basically looking at what is the multiple access technique, why we have yesterday we only discussed what is OFDMA, that is downlink, and SCFDMA, which is uplink. So basically downlink, as we mentioned now, it is from the eNode B to the mobile, and uplink will be from the mobile to the eNode B. So we looked at this, but we didn't go through why we require OFDMA, what is the sort of advantages when compared to the previous generation multiple access technique what we had, and why we are going a different access technique called SCFDMA. It is actually, we cannot call it as a different access technique. It is mainly the same OFDMA with a power efficient methodology. So we'll look at that. What do you mean by power efficient and all these things? We'll also look at how we are increasing the data rate in LTE air interface, and also look at the channels, the different sort of the frame structure and how the frequency has been designed. So that's what our main focus will be. So before going through that, so yesterday we discussed about this LTE, evolution of LTE. So we have also gone through the network overview. We'll just go through that now. So we will be focusing on the air interface part here now, and then we'll continue tomorrow also, because this becomes the crux part of our discussion. So that's what we'll be trying to do in day 3 as well. Now, just to give you an overall picture about yesterday's discussion, this table gives you a nice sort of an explanation with respect to this. Just a second, I'm just checking whether anyone who's there in the meeting who needs to be given an access. Okay. Ajay, you have any doubt? You have put your hand up, so I just wanted to check. Okay.
Vignesh.
Yes. Yeah, Hari. Tell me.
Hello, Vignesh.
Yes.
Yeah, Hariom this side.
Yeah, Hari. Tell me.
Can you give a quick review on this LTE architecture on bearer channels like this?
You want me to explain again the bearer channel?
Yes.
Okay, I'll do that. I'll do that in our. Anyways, I'm going to do the architecture again. I'll explain those things as well. Okay.
Okay.
Right. So I'll come to whatever Hariom has mentioned. I'll come to that. I'll just finish this quick recap, and then I'll come to the bearer side. So we looked at various generations. We started with 2G, then we moved towards 3G. We also had some discussion on 4G, not completely, but on an architectural point of view. Now, the main thing what I think some people have got some confusion is, what do you mean by multiple access technique and modulation scheme? So these are two different entities. So we have to clearly understand what does this mean. An E-node B, okay, or a base station, what we call it as base station, has to share its frequency among multiple users, correct? So this is called as multiple access technique. Accessing this E-node B from the mobile, because we have multiple mobile users here also. So how we are doing the access in 2G, we are using something called TDMA. That means each user is differentiated by having something called time slot. Okay, so the frequency remains constant, but the time will be varying for each and every user. The maximum time slot possible in 2G was 8 slots, 8 time slots. Okay, so now similar to that in CDMA, what we are doing is we are differentiating each and every user not by time, not by frequency. It is purely based on code. Okay, so this user might be having a different code 1, let's say. So this user will be code 2, this user will be code 3. Okay, whereas in LTE, as we discussed, it is OFDMA in downlink and SEFDMA in uplink. So I'll explain about these things today. So I don't want to get into those aspects now. The next important aspect is in wireless medium, one is multiple access technique. The second part is bandwidth, which remains constant throughout that particular generation. So 200 kilohertz is the bandwidth which was allocated for 2G. In 3G, the bandwidth allocated was 5 megahertz. And in 4G, it is a scalable or a variable bandwidth starting from 1.4 and goes up to 20 megahertz. In LTE Advanced, we have bandwidth which is allocated up to 100 megahertz. Okay. The next important factor was about the modulation scheme. In GSM, it was GMSK modulation, that is Gaussian minimum shift keying. And in Edge, we had both, which is GMSK and 8PSK. That's why we call it as adaptive modulation and coding scheme, AMC. Okay. Whereas in 3G, the downlink direction we had
Hello.
QPSK. QPSK stands for quadrature phase
Hello.
shift keying, and in uplink we had
Hello.
BPSK. So remember this. This
जी
was only in WCDMA.
बहुत बढ़िया.
Okay. In
कुछ नहीं ट्रेनिंग.
HSDPA, the modulation scheme. So this
वायरलेस
downlink
सॉरी
got
गई
upgraded to
तेरी हुई थी
HSDPA
10 दिन
here, and the modulation scheme got upgraded to something called
गंदा
16
हो रहा है
QAM.
करनी तो दीवाई ना.
Okay. So how many bits we have in 16 and QPSK? I'll anyways repeat it because we are
रिकॉर्ड
anyways
काल
discussing
मैं
those
कितनी नहीं
modulation
काल
scheme in
कितनी
it.
थ्री रिकॉर्ड आज
So
कालता
just
हूँ
remember these things so that it
काम
will help you whenever we are discussing this. And the next
5
one
दिन
is
रही 5
about
दिन रही मेरी
the
3 घंटे
HSUPA,
बस.
which is QPSK modulation. Now, the same thing, if you look at LTE, we have
हाँ
three different modulation technique, which is adaptive in nature, QPSK, 16 QAM and 64 QAM,
फंडामेंटल्स वगैरह
in downlink direction, that's very important. In uplink, we have, as of now, we see a lot of implementation with respect to QPSK and 16 QAM. There's only one channel, I'll come to this, just remember this, there's only one channel which is called PH, Physical Hybrid Indicator Channel, which uses a modulation scheme which is called as VPSK. Okay? It's called VPSK. Now, let's look at architecture point of view. 2G had circuit switch for voice and packet switch for data services. There was no change in the architecture. Even in 3G, it is circuit switch and packet switch. Whereas in 4G, whether you are doing a voice or video services, everything comes under an IP core network. Okay? And we have a voice services. For voice services, we need a separate sort of an infrastructure which is called as IMS, IP Multimedia Subsystem. Now, band is country specific. So typically in India, we went with 900 and 1800 megahertz. As we discussed yesterday, what are the sort of features inside 900, 1800? If you go with 900 and compare it with 1800, 900 has lesser frequency and wider sort of wavelength, so it can travel a larger area. 18 megahertz will travel less area. 21 megahertz will have still lesser area. That's why you can see that 3G coverage will be less than let's say the 2G coverage area what we have. And similarly, as and when you are increasing the frequency, the coverage reduces. So basically, if we are increasing the frequency, the disadvantage is the coverage reduces, but the advantages is you get a bigger channel bandwidth. So bigger channel bandwidth, for example, you can see here this 20 megahertz, 15 megahertz is possible only when you go for higher channel frequency. Now, these are the peak data throughput what we got, 384 kbps. We also got somewhere around 21 mbps in 3G. We could achieve 84 mbps, but sort of we didn't see any sort of implementation in 84 mbps. Basically, we moved towards the 4G where it took over from the HSPA technology. Now, just coming back to what Hariom had mentioned about the bearer point. So first, we will see how the LTE architecture is. Usually, we have something called UE here. So this is the air interface. So here you can see here, this is the E node B, what we call it as the radio network, right? So this particular part, what we have is called as UTRAN, UMTS Terrestrial Radio Access Network, or it is called as LTE. Both are one and the same. So it is called UMTS Terrestrial Radio Access Network. Just draw it again. So we have mobile. This is air interface. We have E node B here, and this particular system is called as UTRA. Okay, or it is also called as LTE. Now this E node B, on one side, I just change the pen. So you can see here. So on one side, it is connected to MME. Why I put it in dotted line? Because this is purely taking care of signaling, or what we call it as control plane.
Hello, sir.
Yes.
Sorry to interrupt, sir. I'm not getting the screen, sir. Only black screen is there. Can I send the request again?
Yeah, you can disconnect. Are everyone able to see whatever I wrote?
Yes.
Okay. Who is not able to see? I am not able to see. Who was the participant who told me that he is not able to see?
Manish. Sir, Manish. Sir,
Okay,
can I disconnect?
Yeah, can you disconnect and connect back, because everyone else are able to see that. So can you just disconnect and connect back? I think you will be able to see, and then you can acknowledge me. Okay.
Okay, sir. Right.
Thank you. So the problem is, again, I have to write it. That's fine. So I'll just write it again. So E node B we have. So this is the radio access network. So on one side, it is given to something called MME. MME takes care of only signaling. That's why this interface name is called S1C. Okay, or it is also called S1 MME. Okay, both are one and the same. So it is called S1 interface. Yes. Yes, Manish? Hello? Hello? So everyone are able to see this, whatever I am trying to sketch it here, right?
Yes.
Okay, fine. So the other side is, we have one more S1 interface. This is called S1U, which is user plane, right? So this is given to S gateway. We yesterday looked at what is S gateway. Then it is given to P gateway, and then this is given to, let's say, for simplicity purpose, I'll put it as interpreter. Now from P gateway, for our voice over IP services, which is given by the operator, which we call it as VoLTE, we require a separate infrastructure which is called as IMS. Okay, and this put together, what do we call this as? We call this as EPC. Okay, EPC, not EPS, EPC. This is called as LTE. So it is also called as UTRA, UMTS terrestrial radio access network. Sometimes in literature you can see this also as SAE. Okay, system architecture evolution. Now what we have to understand here is, what does this bearer means and what is the impact of this bearer. So we have something called HSS also here. I'm not writing that because HSS doesn't take care of much on the bearer side. So just to explain about the bearer, see, basically bearer means a connection, a logical connection from this mobile till the P gateway. Because if I don't have a logical connection, I cannot do any data transaction. This connection is called as bearer. Okay, you're getting my point. What do you mean by bearer? Bearer means a logical connection, logical end-to-end connection. Okay, why I'm saying logical? Because physically I cannot have a connection between UE and P gateway. So UE is connected to P gateway via multiple interfaces. So here, this is called as, this particular bearer is called as radio bearer. Okay, this particular bearer is called as radio bearer, right? This particular bearer, what we can see here, this is called as between E node B and MME and S gateway. Put together, it is called S1 bearer. Okay, S1 bearer. And here, this interface name, as you remember, it is called S5 or S8 bearer. Okay, and there was one more important interface here. If you remember, E node B to E node B interface is called as X2 interface. So please remember all these interfaces are very important. So a bearer, this bearer, what we call it as a logical connection, typically is called as end-to-end connection is EPS bearer. Why it is called EPS? The LTE plus the core network put together, it is called as EPS. EPS stands for Evolved Packet System. EPC stands for Evolved Packet Core Network. And you know about all these things. So LTE plus EPC put together, it's called as EPS. So this particular bearer, what we have, is called as EPS bearer. Okay, the EPS bearer consists of how many bearers? The radio bearer plus S1 bearer plus S5 bearer. And for simplicity purpose, I am putting as S5. It can be S8 also. Okay. So only when I do this bearer connection, then only you can make any sort of transaction with the network. That means just a second. Yeah. So whenever I'm doing transaction, let's say if I'm doing a VoLTE call, if I'm doing a WhatsApp, or let's say I'm checking my Gmail, for everything I need to have an end-to-end connection. Okay, you're getting my point about bearer. So this is called as bearer. Now in bearer, we have two types of bearer here. One is called as default bearer. Another one is called as dedicated bearer. Okay. Now why we have done two different bearers? That is because the moment the mobile is switched on, which we call it as power on process. So the moment you switch on, the UE has to register with the network. So for that, we need to do some sort of data transaction. That means there is something called authentication, which we do with MME. Okay. And then we need to do and come to a stage called as idle mode. So for this sort of data transaction, we don't require any sort of guaranteed bitrate across the network. So typically a default bearer will have something called NGBR. That means the bitrate fixed between UE and P gateway. Whenever you switched on your mobile and getting into idle mode, we don't fix any data rate. So that's why we call this as non-guaranteed bitrate, and we put all the users into something called default bearer. Okay. So remember this, the moment you switch on your phone, you will be having an establishment of an EPS bearer, and typically it will be a default bearer. Okay. Now, let's say you want to make a voice call. So whenever you want to make a voice call, your bit rate is always fixed. Typically, it will be somewhere around, let's say 12.2 kbps, or if you want a higher data rate, they may fix it to 64 kbps. But this data rate will be fixed in uplink also and downlink also, both sides. Okay. So I need to fix the data rate. So that is called as guaranteed bit rate. So in a dedicated bearer, a connection will be given in such a way that your bit rate will be fixed. So whether it is a voice call, or let's say you can also do a video call with 4G. So these kind of services will be categorized under dedicated bearer. Now there is a chance that let's say you are watching a video through an app like GeoTV. Okay. So this will also require a guaranteed bitrate, right? But an operator like Geo might not use that as a dedicated bearer. It will use it as a dedicated bearer. It will not give the guaranteed bitrate for these kind of video transaction what we are doing inside network. So what it can do, it can also push the users to something called NGBR, non-guaranteed bitrate. That means whenever we are in a dedicated bearer connection, you might be in guaranteed bitrate for, let's say, VoLTE call or a video call. If you are watching some videos, you might be dedicated bearer itself, but you might be pushed to something called as non-guaranteed bitrate. That means the bitrate will not be fixed by the network. Whereas in default bearer, it will always be non-guaranteed bitrate. Okay, there is no change in this. Now, in this EPS bearer, yesterday what we saw was, typically we will have one default bearer for what? For doing all your internet services. For all your internet services, we are having default bearer. That means the traffic will be non-guaranteed bitrate. Okay? There is, let's say, suddenly you want to make a VoLTE call. Now, from now onwards, I'll call it as VoLTE because we are doing a voice call using an LTE network. So if we are doing a VoLTE call, this requires a different set of priority. So what we do for this, we first create a default bearer. Why default bearer? Because default bearer is created for IMS signaling. So first thing is we need to do signaling first and then the traffic flows. So this signaling will always be NGBR, and as we discussed, the QCI value of this particular default bearer will be typically what is the value? 5, and it will be priority 1. Okay. If we are doing, once we set up the call and if the signaling goes through, the next thing is we need to set up a dedicated bearer for the voice to flow through the network. That is also through IMS, but this will be a guaranteed bitrate. And if you remember, it had a QCI value of 2 and it had a priority of 2. And this will be typically what we see. It can be set to priority 8 or priority 9, or it can also be 7, 8, 9. So anything might be possible. So default bearer will be typically used for internet services and also for your other services. And if you are doing a VoLTE call, again there will be a default bearer for purely IMS signaling with priority 1, which is non-guaranteed bitrate. And whenever we are doing a voice call is set up and you are doing a voice call transaction, you will be given a guaranteed bitrate with a QCI value 2 and priority. Okay. Any doubts in this?
No. Hello?
Yes.
Yeah.
Okay, so I will move forward. If there are no doubts, I will just move forward. Just a second. Okay. So taking this particular concept now, I'm moving forward. I'll just share my screen. So any doubts in these concepts, what we discussed now? So this particular revisit, what I've done is just to make you understand what are the sort of modulation scheme we are using, what is the modulation, the multiple access technique we have, what is the bandwidth we have, architecture, you know, what is the advantage now? It is purely all IP core with having an extra IMS infrastructure for VoLTE services. So these are the things which we have to remember so that we can move forward with LTE and interface. Okay. So we already discussed about EPS architecture. I'll just go through that once again. We look at what are the different sort of FDD and TDD band. Now we looked at initially about what do you mean by downlink and uplink. So downlink is always from the E node B to the mobile, and uplink is always from the mobile to the E node B. Now in this connection, why we call it as duplex? Because the downlink and uplink happens simultaneously, right? So in LTE we have two options. Either we can have a separate frequency for downloading, a separate frequency for uploading, and this particular concept is called as FDD. Okay, so there is a separate, or we call it a symmetric communication, where there is a separate frequency for download, and separate frequency for upload. Now there is one more thing, wherein I have one single frequency, let's say F1, which will be used by a mobile for both uploading and downloading by taking different time, and this is called as TDD, time division duplex. So there are set of frequencies given by the standards that which has to be TDD, and set of frequencies which are given by the standards for FDD as well. So we look at those bands. We look at what are the factors which are sort of impacting the throughput in LTE. We already saw that, let's say we had 200 kilohertz in 2G. We are moving towards something called 20 megahertz in LTE, for the simple reason that as and when we increase this carrier bandwidth, we call this as carrier bandwidth, we will be increasing the data rate as well. So like this, what are the other different factors through which we can increase the data rate? We have a nice representation, so we'll go through that. We look at what are the different sort of UE categorizations what we have in LTE release 8. As you can see, yesterday also we discussed this. Release 99 was the first release of 3G. Release 8 is the first release of 4G, and release 15 is the first release of 5G. Okay, so we'll be sticking ourselves to what are the release 8 UE categories. This concept becomes very important for us to understand, because everybody yesterday were kind of asking about what this OFDMA means, what this orthogonality means with respect to this OFDMA, why we are something called SCFDMA in uplink, why we have different sort of multiple access technique in uplink and downlink. So we look at this, okay, and we'll look at each and every frequency domain aspect and the time domain aspect of LTE, because in LTE it is mainly we have to look in two dimensions. Earlier, if you look at in 3G, it was either time, either code, or either frequency. It was only one dimensional. But in LTE, we need to look at the frequency perspective also and the time perspective also. So what does this mean? We'll come to that. And last one, we look at what do you mean by reference signal and how it sort of impacts our network. Okay. So everyone I hope are familiar with these architectural entities what we have got. See, yesterday we discussed E node B is the only entity which is there in the radio access network. So earlier we had in 3G which is called as node B and RNC. So now it's called sort of being a single entity now and called as E node B, evolved node B, and the E node B to E node B interface is called as X2 interface. As you can see, it is also called as evolved UMTS terrestrial radio access network. So on one side, it is given to the control state, which is MME, mobility management entity. As we discussed, what does this do? This is purely taking care of control or signaling with respect to each and every users. Okay. So what it basically does, it takes care of something called tracking area. It takes care of something called as authentication. So like this, there are a lot of responsibilities given to MME with respect to control. When it comes to traffic, it is handled by these two entities, which is S gateway and P gateway, which is serving gateway, similar to what we have called as SGSN, and P gateway, similarly what we have something called as GGSN. So we can make a comparison and we can say that it is similar to SGSN and this is similar to GGSN. Okay, and PCRF and HSS are typically used for your, let's say HSS is used for your user profile database management, and PCRF is used for mainly for the billing sort of applications. So we are mainly concentrating now on the eNode B or mainly on the air interface. Okay, I hope before this everyone are familiar with all these entities and whatever the other concept what we had with respect to the bearer configuration, okay, and quality of service framework. So these are the things which comes with respect to radio as well as core. So now we will concentrate more on this side, so that this is where our actual job lies in. So this air interface, what are the parameters we need to take care of? Okay. So let me move to the first one, which is about frequency. So this is one of the thing which we can say it's not a limitation, but the shortcoming of LTE, because in LTE, the frequency or what we call it as spectrum, is not harmonized. What do we mean by not harmonized? That means each country has an entitlement to use their own sort of frequencies. So we have one sort of frequency, duplex frequencies, that is FDD. As I told you, FDD means it has a separate frequency for uplink and separate frequency for downlink. Okay, so it has a separate channel for uploading your data and separate channel for downloading your data. Okay, so you can see here in LTE there are around, they have mentioned 32, but it is not according to the sequence. So there are a lot of bands which are available where we have an FDD. So typically you can see here in Geo, we could actually see they were using 3 different bands. That was band 3, band 5, and there was one more band in TDD. I'll come to that. So in TDD, we were using band 3 and band 5. You can make a difference here. Always the lower range of frequency. See, you can see here, this is the lower range of frequency and this is the higher range of frequency. Always the higher range of frequency is always given to eNode B. Okay, and the lower range of frequency is always given to UE. Okay, why is that? Because UE has limited power. UE has limited power and eNode B doesn't have any power constraint. So that's why whenever you are going for higher frequency, it requires higher power. So it is usually, you see a typical trend here, that the higher range of frequency is given to eNode B, the lower range of frequency is given to UE. Similar to that, here also you can see the downlink has the higher range and the uplink has the lower range. Okay, and as we discussed earlier, the 800 band, this is called 800 band or 850 band, this will have a higher coverage when compared to the band 3, which is 1800 band. Okay, 1800 megahertz. But the advantage in 1800 band is it has got a bigger space, or the carrier bandwidth allocation can be more when compared to 850 band. Okay. Now, one more thing we have to understand here is the duplex separation. As and when you increase the frequency, the duplex separation will also increase. So let's take an example. See, this particular band, which is called band 1, if I'm not wrong, this, I think this is also used for 4G for BSNL. So this particular band is called as 2100 band. So you can carefully see, I'll just note it down here. In 2100 band, we are using 1920 to 1980 and 2110 to 2170. So this is, sorry. So this is used for download and this is used for upload. Okay. And you can see here, there is a gap between this upload and download. This particular gap is called as duplex separation. Okay. Duplex separation. So this duplex separation will be high if the frequency is also high. You can see here the duplex separation is around 190 megahertz. Okay, 190 megahertz. But if you look at, let's say, the band 3, which is 1800 band, the duplex separation is somewhere around 95 megahertz. So as and when you decrease the frequency, the duplex separation also decreases. You can see here in 850 band also, the duplex separation is somewhere around, if I calculate, it is 9 minus 4, 25. Yes. So 25 megahertz. So you can see here, as the frequency reduces, the duplex separation also reduces. As the frequency increases, the duplex separation also increases. So this is up to the country or the regulatory bodies, what sort of spectrum they need to allocate. For example, in the US, they have gone with somewhere around somewhere around, I think it is this particular band also they have in Verizon. They also have this band, that is 800 band. Okay, they also have this band, 700 band. So if you look at the bands in LTE, it is not harmonized. Each country has its own rights to select these bands, but only ITU has given guidelines about these numbers. So these numbers and these sort of range what we have remains fixed. Only thing is this frequency keeps on changing from one country to another country. Okay. So this is about FDD. So let's move to TDD. So in TDD, we see a lot of deployments being taking place in band number 40.
Vignesh,
yes.
Can you please back on previous slide?
Yes, sir. Tell me.
Actually, that's 922, 900, 1908. This is the full band. Suppose there is two operators, voice operator. Then
Okay.
they will give the separate frequency for the, suppose 920 to 925, like that.
Correct. So I'll just give, I'll just give you an example here. See this. Let's say, let's take an example of this first band, 1920 to 1980. Okay. So how much gap you have got? 60 megahertz. So this is a channel which has 60 megahertz. Let's say the regulatory body in India thinks that we will allocate each operator 20 megahertz. Okay, each operator 20 megahertz. So now I can have only 3 channels. You're getting my point? 20
Yes.
megahertz means I can have only 3 channels, means I can allocate to 3 operators. Fine. So one operator will be getting 20 megahertz, another operator will be getting another 20 megahertz, another operator will be getting another 20 megahertz. So similarly, in downlink also, the corresponding downlink frequency will be allocated to those operators. Okay. Now, if I decide, let's say an operator, or I'll just erase this. If we decide, for example, if you remember, this particular band is first used for 3G. It was not used for 4G. Nowadays, we are using it for 4G by actually tearing down the 3G network and using it for 4G. That can also be possible. But this was the first band which was used for 3G spectrum. So in 3G, the maximum bandwidth was 5 megahertz. So we could have got 60 divided by 5. So around 12 channels can be created in 3G. Similar to that, even in 4G also we have this particular bandwidth, isn't it? So if a regulatory body thinks that we will not give 20 megahertz, we'll give 5 megahertz, then we can have 12 different channels instead of having only 3 channels. So this is up to regulatory body how they need to allocate these channels to the each and every operator based on the auction, based on the spectrum allocation. All these things might take place. I hope it's clear now.
Yes, yes. Thank you.
Okay.
Yeah, Vignesh.
Yes.
And this spacing is also different in different bands, like spacing between uplink and downlink bands.
You're talking about duplex separation?
Not duplex separation. This difference between like 1980 to 2110. It's 30 megahertz. Band
Okay,
gap.
see, that's fine because see, I'll just tell you how this has been done. Let's say when I say 1980, 1 minute. See, when we say 1980, don't check with the next 2110 because 2110 is the starting frequency, correct? So this 2110 is corresponding to 1920 here, okay? And this 1980 is corresponding to 2170. So now this, if you see, the gap is 190 megahertz, and this, if you see, the gap is 190 megahertz. Okay? So we are not seeing this separation because the separation is from this side to the last. We are seeing the last bit of frequency in the 1900 and comparing it with the last bit of frequency in 2170. You are getting my point?
We have to check this out.
Correct. So let's say 19, I'll just give you an example, one more example so that we can understand things better here. Let's say a BSNL, I'm just taking the, yeah. Yeah, now I'm able to write. So let's say BSNL gets from 1920 to 1940, okay? This is the channel number 1. So in what direction this is? This is in uplink direction, okay? The lower frequency. Now BSNL will also get the downlink frequency between 2110 and 2130. It cannot get 2150 to 2170. That is not possible. It has to be a paired frequency itself, because as the standard says, there should be a gap of 190 megahertz as a duplex separation. Then only the frequency or the oscillator will work, or else the oscillator will not work. Okay. Okay, you are getting my point now. Is it clear?
Yes.
Okay, thank you. So I'll move to the TDD band now. Yeah.
Yes, if FDD is there, then why we require TDD?
Okay, I will come. Just hold on for a second because I just finished TDD, and then we'll look at some of the pros and cons of what do you have FDD and what do we have TDD. Because we have to really see this, because in 3G we didn't have, or nobody opted for TDD. They opted for FDD because always we designed our network for symmetrical communication, because our main intention was voice services. Voice is a symmetrical communication. So then we went for FDD. Now, if you look at internet-based applications, internet is not always symmetrical, isn't it? See, we download more, we might not upload itself. So because of that, they also came up with TDD, and there are other sort of advantages also with TDD. There are disadvantages or challenges in TDD. That I'll come to it. To answer to your point, a quick answer to this is, both have their pros and cons. It is up to implementers. So standards define both FDD and TDD. And it is up to all the operators and the regulatory body whether we need to go with FDD or TDD or not. So after TDD band, so I'll move to TDD now. After TDD band, I have put a table wherein we make a comparative analysis between what is FDD and what is TDD, what are its benefits and what are its shortcomings. Okay. So now let's look at TDD. In TDD, if you look at here, it is only one single frequency which is mentioned for both uplink and downlink. That means Geo has this particular works on 2300 band. It has actually got 20 megahertz plus 20 megahertz. Two channels it has got. Okay. So now for simpler purpose, I'll just mention it as 20 megahertz because we can understand things better. So if you look at it, the gap is, it is 100 megahertz. Okay, the total channel bandwidth is 100 megahertz. If we consider the highest bandwidth available in LTE is 20 megahertz, we can have 5 channels. Okay, 5 channels in 2300 band. In this, 2 channels are already occupied by Geo. So they have most of the circles are having 20 plus 20, 40 megahertz. It's 2 different channels. It is not a single channel because there is no 40 megahertz bandwidth itself available in LTE. It's 2 different channels which are there. Now the advantage here is I did not have 2 different frequency for uploading and downloading. That is first advantage. The second advantage what it has got is we don't require something called as duplex separation. So in a single frequency, I can accommodate both our uplink as well as downlink. Okay, so that's one advantage of having this. But there are some challenges with TDD because there are some design complexities when we come to TDD because we need to allocate this frequency for certain amount of time, let's say T1 time for upload and T2 time for download. And this is also kind of defined in 3GPP specification. That means how much time should I allocate for upload, how much time should we allocate for download. We have something called TDD configuration. So I'll come to this when we go for configuration. So all these are sort of predefined in standards, and based on that, operators have a choice to take those configuration and implement those configurations. So you can see here the design complexity is more, and there is one more sort of challenge in TDD because let's say I am doing download with 2300 band, okay, at one instant of time. In the next instance, whenever I am doing an upload, there is a gap, and this gap is called as special subframe. Okay, we call it as special subframe. That means there requires an overhead information to switch from download to upload. So that means there will be an impact of throughput whenever we are doing TDD connection. So TDD has a limitation with respect to throughput because of this switching of download to upload within the same frequency. Whereas in FDD, we don't have all these challenges because it is going in its own direction. So it is like, let's say you are in a highway, you have a divider and you have a separate path for one-way traffic, the separate path for coming from another way traffic, right? So let's say there is a highway, there is a divider here, and there is a separate traffic going on this side, separate traffic coming from this side. So this is FDD. Now advantages, you need not control this because uplink is happening in its own way, downlink is happening in its own way, but only thing is you require so much space, isn't it? You require so much space to do this FDD. Whereas in TDD, it is a one-way traffic. So that means if I'm allowing a user to transmit in download, upload cannot take place, right? So upload will take place only when I stop this download and then allow the upload. So how we do this, we need to take care of this, but the advantage here is the space taken by TDD configuration is much lesser when compared to FDD configuration. Okay. Now you have seen what are the differences, what sort of features are there in each and every sort of duplex technology. Now we look at the difference. Any doubt so far?
Vignesh, you can go,
Yes.
go back.
Okay.
Actually, if the voice quality, the voice quality will be good in LTE, right?
Okay, we can say that because it is a symmetric, and we can say that yes, but you always see we are also using 2300 in Geo, and we are also using, I think if I'm not wrong, 2600 in BSNL. Is it correct? Is
I
it this
have less
band which we are
idea.
using? If am I correct? BSNL is using this band. Okay. So BSNL is using 2600 band and Geo is using 2300 band, and we are getting good voice quality. So that is why if you look at the TDD configuration, TDD has certain configuration where in we can give some sort of priority to all these VoLTE services. So that's possible. But if you look at generally, yes, FDD works well with symmetric based communication. For an asymmetric based communication, or let's say in sort of some sort of efficiency, TDD has an upper hand.
TDD is the best utilization.
Correct. So the resource utilization is best in TDD, because let's say if I'm doing only internet based application, my uplink might not be utilized efficiently when compared to downlink, isn't it?
Yes.
So that is why if you look at it, most of the operators will, you can see the example of Geo as well as BSNL. So BSNL has 2100 band in FDD and 2600 band in TDD, let's say like this. So they might give all the users who are doing internet services in TDD and maybe push all the users in VoLTE in FDD. That this can also be designed. Okay, but this is not always true. We can have VoLTE services here also and internet services here also. But as generally we can say, because of the paired frequency, VoLTE services might be lesser complex design in FDD when compared to TDD. Is it clear?
Yes, yes.
Okay, any other doubts?
Just can you come back to FDD translate?
Okay.
In this band number 29 and the 32 is having a single set of frequency, how the uplink and downlink will happen?
Okay, see, the basic thing here is with respect to this, right?
Yes.
Correct?
Yeah.
Okay, so actually what is happening is there are certain things with respect to these, we are, if I'm not wrong, these bands are sort of having harmonics with something called L1 GPS. So even though they have mentioned these frequencies, typically we are not using these bands. The standard says these are being used with 700 band and let's say 1500 band. But typically, since they are actually having an interference with the harmonics of L1 GPS, even though it is mentioned in the standards, we are not typically using it. Okay. Yes.
In band 31, the downlink frequency is lesser than this uplink frequency.
Okay, very good. So I was just seeing whether anyone had this doubt. See, this one you're talking about, right?
This 30 also.
Correct. So if you look at this, these are all having some sort of a connection between these GPS harmonics. The global positioning system frequency also having a receiver frequency, right? So GPS has a receiver which is coming from the satellite. These frequencies are sort of interfering with these frequencies. That's why they have made uplink, let's say, contradictory to what we typically have, something like this here. So that's why these sort of frequency, when they developed in standards, the L1 GPS was not being utilized. L1 GPS was already being utilized. So they have given this in standards. Since it is actually having a harmonic connection with the L1 GPS connection, basically we are having this with respect to uplink or vice versa with respect to downlink. We have not seen any sort of implementation being done. Standards have given these sort of band numbers, but we typically see these are being implemented. But the reason, quick answer or sort of the whatever doubt we have with respect to this, the answer to this is it is sort of having an interference with the harmonics of L1 GPS, the GPS connection. Is it clear?
No, come again. No.
Okay, see, the basic idea is, see, if you look at this particular frequency, so what you mentioned is this should have been downlink and this should have been uplink, correct? Now, if you look at it, this is downlink now. That is the reason being that this particular frequency is having some sort of a connection with the GPS receiver signal, okay? In GPS receiver signal, we have multiple frequencies designed for even GPS receiver. So it is sort of having an interference whenever, see, GPS receiver means it is mainly concentrating on the downlink direction side here, right? So in satellite communication, you can see here, in satellite communication, it is always the sort of vice versa of what we have is in cellular communication. In cellular communication, I'll just take a white sheet here. In cellular communication, the downlink should have higher frequency, uplink should have lower frequency, correct? In satellite communication, the satellite has lower power. So that means the downlink will have lower frequency, uplink will have upper frequency, okay? So that is the reason that most of the frequency what you see here, these are also used for satellite communication, for long distance communication. So what is happening is, this is sort of being interference with the cellular communication. So that's why we have given more like a satellite communication, wherein satellite communication has uplink larger or higher power frequency, downlink has lower power.
So these bands are basically for satellite communication.
Yes, it was actually designed for satellite communication. They have put it in our band list only because this FDD and TDD bands are not for LTE. It was there for 3G, it was there for 2G, it was there for satellite communication, it was there for GPS communication, any sort of a spectrum wherein we are using it for wireless communication. You're getting my point? So that's why typically we don't use those frequency, even though it's there in the standards. The regulatory bodies typically, we see a lot of implementation with the frequencies which are there, what we discussed, right? Like the 2100 band, 1800 band, the 850 band. And if you really see, the 1800 band and the 850 band were already being used in our 2G network, right? This was used in 2G. This was used in 2G CDMA. So the same thing has been sort of used in LTE, and typically we call this as reforming. That means we are using our existing 2G spectrum and using it for 4G spectrum. So if we see here, maybe they would have mentioned here as E-Utron operating band, but if you look at any sort of document, these are the typical bands we had from our 2G days itself. Okay.
So same 2G band is allocated for 4G, whether it will not interfere with the 2G signal.
Okay, see, the basic thing what I mentioned here is, for example, let's say for this we need to understand the sort of auction which took place. When initially auction took place for 900 megahertz and 1800 megahertz, okay, this was somewhere in the timeline of 2000, I think 1800 took place in the year 2008. Again, when the 4G auction took place, the regulatory body, what they did was, they made this license not restricted to 2G. You can use it for 4G also, but the condition is If you use it for 4G, we cannot use it for 2G. Okay, as you pointed out, it's correct. If I use it for 1800 in, let's say, in this particular cellular area, if I use this 1800 band for 4G, we cannot use it for 2G. Okay.
Okay. Yeah,
But
in this case, provider wants to establish the new network, 4G network.
exactly. So
He can dismantle the 2G equipments and he can, if you install the 4G equipments, he can upgrade.
correct. So that's why we call it as refarming. Usually you see this in literature called refarming. What they mean by refarming context here is we farmed using 2G frequency. Now we are refarming it using 4G. Okay. So sometimes you might see this is just extra information which we understand with 4G. In 1800 band, if you are using it for 4G, we can simultaneously use it for 5G also. This is being done in most of the operators in the sort of other markets here. This concept is typically called as DSS, dynamic spectrum sharing. So we share the spectrum of 1800 band for 4G also and 5G also. This is being taken care. In India, we don't see this implementation, but we have this, and standards have also been developed for this, wherein we can have a 4G infrastructure being implemented for 5G simultaneously. So this can also be possible, but with respect to 2G and 4G, we cannot have one spectrum being utilized for both the technologies. So that's not possible. Okay. So for the simple reason, as here we pointed out, it is because of the interference. Okay. Right. So any other doubts? Okay. So I will move to this particular slide wherein I think there were few doubts about what do you mean by FDD, TDD. I think everyone understands now. What are the differences? What are the pros and cons? We'll understand. So if you look at paired spectrum, the first feature, here we require a paired spectrum. Here we don't require a paired spectrum. It's a single one. Interference, very important. Interference between neighboring base stations is less because the transmission, the TX and the RX is done in a separate frequency. In TDD, the neighboring base stations and the existing base stations will have a lot of interference, and we need to mitigate this by doing some sort of technique. So we'll come to that, how it is being addressed. Hardware cost. So diplexer is needed. The cost is higher. Here it will be typically lower because there is no diplexer here. Guard period. There is no guard period provided here because there is no switching of downlink and uplink frame. I'll come to what do you mean by subframe. I have not come to this, but just remember there is no guard. That means there is no gap between downlink and uplink. Here there is a gap, right? And channel reciprocity, channel characteristics is different in both directions as a result of use of different frequency. Now, this is one of the advantages what TDD has got, because the channel condition or the radio condition, if we understand what do we have channel condition in uplink, the same condition can be given for downlink as well. So this is one of the advantages of having TDD. But in FDD, the channel condition for uplink will be different because the uplink frequency itself is different, and the downlink channel condition will be totally different. Okay, so these are some of the pros and cons, or let's say the contrasting views what we have with respect to FDD and TDD. Okay. Okay, any doubts so far with respect to FDD and TDD? Okay, let's move to
FDD.
Yes.
Can you go back?
Yes.
In FDD, that frequency is uplink and downlink frequency is different, right?
Correct.
So there is no guard band required.
See, within FDD, let's say this is downlink frequency, okay, and this is uplink frequency. What it means is, I'm not talking about guard, not the duplex separation. What here the guard period is, since I'm having different path for downlink and uplink, we did not have a guard or gap inside this frequency. Okay, not required.
Okay,
Whereas,
this is, suppose there is uh, 8 channel frequency channel. This
okay,
channel to channel upload in total, there is suppose 8 frequency channel. The frequency
eight
channel.
frequency. You are talking about 8 frequency channel within that particular band.
Yes.
Okay.
So I don't know actually how many channel frequency channel can be created in single band.
See, it purely depends on what sort of bandwidth you have got, right? See, for example, let's take an example here. Let's say 1800 band. In 1800 band, Geo has got 5 megahertz as one channel. Okay, fine. And in 2300 band, it has got 20 megahertz as one more channel.
Yes.
And it has got one more 20 megahertz. But this is TDD. Okay, this is TDD. This is FDD. And in 850 also it has got one more channel which is 5 megahertz, which is FDD. So 5 megahertz uplink, 5 megahertz downlink. Here also 5 megahertz uplink and 5 megahertz downlink. Now these channels, it is separate 5 megahertz and separate. This is separate 5 megahertz and this is separate 5 megahertz. Whereas this 20 megahertz used for uplink as well as downlink, right? So whenever we are switching from uplink to downlink, we require a guard or a gap just to make a user understand that what is uplink and what is downlink. Whereas if we look at this, here I have a separation. This is called duplex separation. But within this 5 megahertz, we don't require any guard period. That's what it means. Okay. Within that particular, yeah.
In 1800, it is 5 megahertz, right?
Okay.
8 megahertz. Maybe there is maybe one voice channel required. Maybe for 2G, it is 12 point something kbps, right?
Right.
Then frequency will be maybe 15 kilohertz.
Okay, I'll come to that 15 kilohertz concept. I'm not come to that, so I don't want to jump into those things. See, just remember this: those subcarrier spacing, what we have, and those things are not related to what we have with respect to FDD and TDD. FDD and TDD talks about a separate frequency for uploading the data and downloading the data. Inside granularity is what you're talking about. 15 kilohertz is taken care by a separate entity called WebDMA.
That means this upload and download channel will be different. Frequency channel will be different. So automatically gap created. That maybe in gap we can use it in other direction or other.
So how we are doing that configuration, I'll come to that whenever we are moving towards TDD, because the guard period concept is only in TDD, not in FDD. Okay, that's what it mentions here. There is no guard period in FDD, but in TDD we have a guard period. Now why we do this guard period, I'll come to that whenever you look at the frame structure of TDD, because the frame structure of TDD is different, the frame structure of FDD is different. Okay. Is it clear?
No.
Yes. Any other doubt?
So in other words, we can say in condition that with their special time frame, with their special substrate in 2400 in TDD, rather than 850 and 1800. We don't require special substrate, we don't require special time slot.
See, there is a subframe concept in FDD and TDD both, but there is no something called guard period. See, the subframe concept, the frame concept, or let's say the slot concept is there in both FDD and TDD both.
That means guard period only occurs in 2400, that is in TDD.
Exactly. Yes. The guard period, not only in 2300, any TDD technology will have a guard period.
Special time slot.
Correct. Yes. and typically, to quickly answer you, it is called a special subframe. I'll come to the special subframe concept whenever we are discussing the frame configuration in TDD. Okay. Okay. Any other doubt? Okay. Let me have a 5 minutes break if you don't mind, because I don't want to get into OFDMA and try to complex situation. So let us have a 5 minutes break, and then we'll start our OFDMA and SEFDMA, because this is quite important for us to understand the frame, understand something called subcarriers, how it has been designed. So that's why I need to take 5 minutes break with respect to this, and then we'll start fresh with OFDMA and SEFDMA. Okay. So
It will be better.
okay, so it's in my watch I can see it's 5:15, 5:17. So 17:17. We'll meet at 17:25. Okay. Thank you. Day-wise content is uploaded in our LMS portal, so you might check that, and any doubts you have got, you can just put it across in the chat window. Please stop me at any point of time, and in case if you are not able to access it also, you can mail me, and maybe we will get back to you on those content access as well, because whatever nominations I've got, those nominations user IDs have been created, and we have shared those LMS link to access you the day-wise content. So in case if you're not got, you can just let me know. Right? Thank you.
So how long that content will be available? Suppose today I seen that uploaded the first day one content.
Right. It will be available. I'll just check with our LMS team and the person whom I'm coordinating with. I think you will be able to see that content, since your user ID is already been there. Till your user ID is been disabled by the LMS portal only, you will not have access to that. Till that time, you will be having an access, right?
Okay. Because at least 7 days
There is
after.
no timeline. See, basically there is no timeline. You can watch it anytime you want, but only thing was, I think there is some restriction with the user ID creation, whatever we have at the LMS portal. So in case if let's say if there are lot many people who are coming, then only we need to check how many users we can sort of accommodate. But as of now, there is no timeline for that.
Okay, it's okay. My side request is, if it is possible, suppose if username deleted, then unable to access. Yeah. Then is it possible to share this PPT to us? Because otherwise,
from Tejas Academy, we are not supposed to share the content as of now. But still, I will just check with our team here, and I'll get back to you. Okay.
Okay. Better you.
As of now, yeah. As of now, it is only through the LMS portal.
Okay. Our request is, please enable the account at least 1 month.
Sure. No, 1 month it will definitely be there. That you don't worry. 1 month it will be definitely be there. That's not an issue, right?
Okay. Thank you.
Okay, fine. So let me start with the next important concept in LTE, which is called as OFDMA and SCFDMA. Basically, it is a multiple access technique which we use in uplink and downlink. Any doubts? I could hear some voice. Okay. So let me just first go to explain about what does this really mean. See, the first thing we have to understand is, I think everybody now understand what do you mean by FDMA, right? Frequency division multiple access, wherein we have sort of unique multiple frequency being allocated to each and every user. This was typically done in 1G. Now, what is the difference? What does this O contribute so that it becomes a more prominent in LTE and widely used multiple access technology, because this is also nowadays used in Wi-Fi as well. Okay. Now O, as I think most of you had yesterday discussed and they were able to get this, which is called orthogonality. Now orthogonality, let's say in mathematical term, everybody understand it is something called 90-degree, unique, everything. So how do I make someone understand, a layman understand, what do you mean by orthogonality? See, this orthogonality concept was not there in LTE itself. We also had it in 3G, where we had something called orthogonal codes. So what do you mean by these orthogonal codes? Just to understand, see, generating a code is not a big challenge, isn't it? So a code is something like a language. So in India, we have so many languages available, but these languages also have a differentiating factor, but it has some commonality also. So for example, if I say Hindi and let's say English, both are orthogonal to each other. Okay. Whereas if I compare Hindi and let's say Punjabi, they are not orthogonal to each other, because both the languages are having lot of similarity, right? Similarly, let's say Tamil and Malayalam are not orthogonal because there is a lot of similarity. Or let's say Bengali and Odia, you can correct me, they have a lot of similarity. So these particular sort of codes are not orthogonal to each other. Whereas if I consider Hindi as a language and English as a language, or let's say a different code, they are orthogonal to each other. So orthogonality means whenever I am actually talking about any sort of two entities, they should be unique to each other. There should not be any similarity. That is the meaning of orthogonality. Now here, what it really means is, when we say OFDMA, earlier what we used to do is, in, let's say, this was my 200 kilohertz channel which we had in GSM, right? So this, what used to happen, this was 200 kilohertz. When we moved to LTE, we increased the bandwidth up to 20 megahertz, right? 20 megahertz. This 200 kilohertz or 20 megahertz is going through the same air interface. So the air interface is not changed. Only the technology is changed, isn't it? So the air interface has the same perennial problem or the perennial challenges like multipath, or let's say reflection, fading. All these are some of the challenges which we face in air medium. Okay. This multipath, reflection, refraction, fading was there in 200 kilohertz also. So in 200 kilohertz, what used to happen is, this multipath channel or reflection challenge, what we call it as, we have a phenomenon here called as inter-symbol interference. Okay. How does it take place? Whenever, let's say, whenever I speak, I take an example here. Let's say whenever I speak in a room, empty room, in an empty room, if I speak, what does I usually get? I get something called as echo. This echo, is it good or bad? If we speak less number of words, echo is good. If we speak continuously, echo becomes a challenge, because the first word will always interfere with the second word, correct? So this is what is really happening even in our air medium. Whenever there is a E node B here and there is a mobile, there are buildings here, right? There are buildings here, there might be some tree here. So there might be a lot of reflection, there might be a lot of fading, and this will create a phenomenon called as inter-symbol interference. That means, this is what I was talking about here, that the first word, let's say this is the first word I'm talking about, will interfere with the second word, right? And this will create an interference or something called as ISI, which is called as inter-symbol interference. Now this ISI is less for 200 kilohertz. Why? because the frequency is less. This ISI becomes high for 20 megahertz. Why? Because we are increasing the bandwidth. So as the bandwidth increases, the inter-symbol interference will be high. Now, to make you understand again what this inter-symbol interference is, that's what I mentioned about an analogy what I took here. Let's say I speak in an empty room, or let's say there is a mountain and I'm just speaking. If I speak only a single word called hello, it will repeat n number of times, right? Because there is an echo which is coming. So if I speak only one word, it's good, because if I don't, let's say I speak from here and there is one more user who wants to listen to my speech, he is listening only one word multiple times. So if he doesn't hear for the first time, there are multiple chance of decoding this data. So this is similar to what we had in 200 kilohertz. So in 2G, when our bandwidth was less, the ISI, the repetition was not an issue because we had less number of data, right? When we are moving to LTE, we are increasing the bandwidth. Why we are increasing the bandwidth? Because only when we increase the bandwidth, we can increase the data rate, right? How we are doing, coming at this conclusion? That is because in 200 kilohertz, if I use, let's say, QPSK modulation, right? QPSK means quadrature phase shift keying. We are using 2 bits, 00, 01, 10, 11, right? So maximum bits are 2. So multiply 200 into 2, we are getting 400 kbps. Whereas if we use the same frequency, same modulation scheme and change the bandwidth and implement it here, the actual data rate will be 40 Mbps. So you can see the change here. With the same modulation scheme, we were able to increase the data rate, right? So the modulation scheme, what we have implemented is same only, but only thing is we have increased the bandwidth, right? So when we increase the bandwidth, the advantage is you can increase the data rate, but the disadvantage of increasing the bandwidth is the inter-symbol interference. That means the interference pattern inside this 20 megahertz will be huge when compared to 200 kilohertz, which will be less. So the interference will be huge here, interference will be less. So how do I tackle this trade-off wherein we need to increase the bandwidth? There is no other choice because we need to have a higher data rate. But how do we tackle this problem called as ISI, which is inter-symbol interference? So to counter this, what standards thought was, why can't we divide this 20 megahertz into small frequencies, a smaller frequency, and the smallest frequency what they chose in LTE was 15 kilohertz. Okay, so this, so I'll just erase it and I'll come back here. So what we are doing here is, just a second. So what we are doing here is, there is no other choice. We have to go with 20 megahertz as our bandwidth. Now what we do, we cut this bandwidth into smaller pieces. Why? To counter something called inter-symbol interference. And the smallest frequency chosen by the standard according to 3GPP specification is 15 kilohertz. Because if we go with smaller frequency bandwidth, ISI will be less. That is, interference will be less. Now what we are doing here is, the 15 kilohertz what we have allocated in LTE, this is the smallest frequency. We call it as sub-carrier spacing. Okay, sub-carrier spacing. So even though it looks 20 megahertz, this 20 megahertz is cut down into 15 kilohertz as the smallest frequency. Now if you look at 15 kilohertz, okay, 15 kilohertz is a very small frequency to do a transaction. So what they did, they grouped this 15 kilohertz into 12 subcarriers. So 15, this is 115, there is one more 15 kilohertz here, there is one more 15 kilohertz here. Like this, they have grouped it into 12. So if you group it into 12, how much you get? 15 kilohertz into 12. How much you get? We get it as 180 kilohertz. Okay. This is called as one resource block. One resource block. 15 kilohertz is called as subcarrier spacing, and 180 kilohertz, because we are putting it into one block, it is called 180 kilohertz or one resource block. You are getting my point? Now, basic definition what we are doing here is, in 115 kilohertz, let's say this is 115 kilohertz, the next 15 kilohertz, whenever there is a peak value here, next 15 kilohertz will start like this. So this will be going like this. Now there is no gap between this 15 kilohertz and this 15 kilohertz. Okay. So this concept, what we are calling it as, this is called as OFDMA, because we are cutting down a 20 megahertz channel to counter something called ISI by putting it into smaller frequencies. And between this 15 kilohertz and the next 15 kilohertz, we are not giving a gap. If we were giving a gap, let's say this is 15 kilohertz and this is one more 15 kilohertz, and we were giving a gap like what we call it as duplex separation, then we would have called it as FDMA, frequency division multiple access. But here we are not giving gap between these 15 kilohertz, and we generate this frequency in such a way that they are orthogonal to each other. So they are orthogonal to each other, and then we get these particular subcarrier spacing. So basically a definition of OFDMA here is a high data rate. Please remember this, a high data rate stream. Okay. What do you mean by this? This is 20 megahertz. A high data rate stream is converted, okay, is converted into a low data rate. Okay, low data rate, very important is low data rate parallel, okay, parallel streams. So this is very important. It is not a serial. So if 15 kilohertz I generate, at the same time I am generating this 15 kilohertz also. So it's a parallel transmission, a slow, low parallel transmission in a orthogonal subcarrier. Why it is called subcarrier? Because this is my carrier bandwidth. We are cutting down that into smaller pieces. That's why it's called subcarrier. Okay. So this is the essence of having OFDMA. So you can see here in the slide also that a big chunk of frequency, that is 20 megahertz, is being cut down into smaller frequency, and the smallest element, which we call it as subcarrier, is 15 kilohertz, and this 15 kilohertz is typically grouped into 12, and the total what we get is 180 kilohertz. Okay. This is the concept, or let's say this is the essence of having OFDMA. Okay. So basically what we are doing, a big bandwidth, we are cutting down into smaller bandwidth to counter something called as intersymbol interference. And remember this, ISI was also there in 2G, intersymbol interference was also there in 3G. Here we did some other mechanism because this was 200 kilohertz, very small bandwidth. So ISI was less when compared to 4G. In 3G, we use something called as complex equalizers to manage this ISI challenge. So OFDMA typically means that the bigger channel is cut down into smaller channel, which we call it as subcarrier, and the subcarrier chosen here is 15 kilohertz, and the subcarrier spacing is 15 kilohertz, which is grouped into 12, and we call that as one resource block is 180 kilohertz. Is this point clear? Any doubt so far?
Clear. A little bit confusion. Actually, this 50 kilohertz is for the per subscriber, right?
Sorry, please come again.
This 50 kilohertz.
Okay, I don't want to jump.
It is for the whatever the slice. This 50 kilohertz slice is for per subscriber, or it is again time.
Quick answer to that is this 15 kilohertz is not for one user. Okay? A user's allocation is not 15 kilohertz. Please remember this. It's a very good question. 15 kilohertz is not allocated to one user or one UE. No, it's not that. The allocation done for each user to just answer you now is 1 millisecond. In 1 millisecond, a user will be allocated 2 resource blocks. Now this resource block, I'll come to this how it has been done, but the resource allocation will be for 1 millisecond. In 1 millisecond, how many 15 kilohertz you get? I'll come to this whenever we are discussing the frame duration. So the quick answer to whatever you asked is 15 kilohertz is not being allocated to one particular user. You're getting my point now?
Yes.
Okay.
Maybe it is shared. Maybe clear in next.
Sure. Okay. Fine. So basic understanding now is why we are going for OFDMA to counter something called ISI. What we are doing to counter ISI, what we are doing is we are cutting down the complete bandwidth into smaller frequency, which we call it as subcarrier, which is 15 kilohertz. But each user will not get 15 kilohertz. How much you get, we will come to that. Okay. Now, just to make you understand, since already there is a topic here of SCFDMA, I just want to cover why we are going with SCFDMA. Now, that means why we are going with SCFDMA, that means there is some sort of drawback in OFDMA, isn't it? Now, the advantages of OFDMA is we are putting parallel streams of 15 kilohertz to counter ISI, and we are able to efficiently manage our higher throughput by having 20 megahertz. Why this becomes important? Because when we come to 5G also, we are using same OFDMA technique. So there is no change. Only thing is this particular sort of subcarrier spacing varies. So I don't want to get into that. So if you remember, OFDMA will be a more efficient technology moving forward, and understanding this becomes more important because this is what the more crux part also in 5G as well. Now, why we go with SCFDMA in uplink? For the simple reason that, see, whenever we are doing this cutting down of smaller frequencies, right? See, this is 115 kilohertz, the next 15 kilohertz, next 15 kilohertz. So we are continuously getting 15 kilohertz here. Now this, whenever it is being done by the transmitter, see, OFDMA, what does this mean? It is in downlink direction. So who is doing this? This is done by E node B. So E node B is having a lot of power fluctuations here. So there is something called power amplifier inside the E node B, and this power amplifier will be having a lot of work because it has to do a lot of power level variation. Okay. So it is like this. It is like, for example, let's say you are riding a bike and you are just increasing your speed and decreasing your speed at constant interval of time. Let's say you are going at 20 km per hour, then you are going 40, then you are going 60, suddenly you go 80, and suddenly you come back to 20. So what impact it will have on the engine? So there will be a lot of wear and tear, isn't it? So the power amplifier will be a very crucial and efficient mechanism, and it will be having a lot of power levels whenever we are doing OFDM. So what is happening? The power level keeps on fluctuating. And here we call this concept as PAPR, the peak, okay, I'll write it here, peak to average power ratio is very high in OFDMA, okay? It's very high in OFDMA. So what is the implication here? Whenever this power amplifier is having a lot of sort of work being done, so in downlink, that's okay. Why? Because eNode B has unlimited power, isn't it? It has very high power to manage this OFDMA. Now, who is doing uplink? Uplink is done by UE. UE has limited power. With this limited power, if I try to do OFDMA, it will have a lot of impact on my battery. So what they did was, in uplink, we are not cutting down into 15 kilohertz. We are cutting down at little more higher sort of subcarrier spacing, or let's say it will be usually 180 kilohertz itself. So now we are not having any sort of PAPR issue because the PAPR averages out and it will become low. So in SCFDMA, the complete data gets spreads out. You can see here, it is not multiple frequency, it is single frequency. So SCFDMA we implemented in uplink only because UE has limited battery. That's the reason it is gone with SCFDMA. OFDMA, we have gone with downlink direction because eNode B has more power. It can tolerate this sort of variation in power amplifier. Even though PAPR is high, it can counter all these ISI effects. So that's why we have gone with OFDMA. So OFDMA in downlink, SCFDMA in uplink because PAPR is low. So SCFDMA is more power efficient. I can mention like this, it's more power efficient when compared to OFDMA. Okay, any doubts so far?
Can we say in SCFDMA there is less trading as compared to OFDMA?
Can you please repeat it? Hello? Yeah.
In other words, we can say that in SCFDMA there is less trading, there is less RSI as compared to OFDMA because there is single carrier.
Okay, see, basically, if you look at characteristics wise, it is having the both, it is doing frequency division only. There is the RSSI or the things has an impact, but also it's talking about the PAPR issue. That means this is having a higher PAPR, whereas this has a low PAPR. Peak to average power ratio will be less. That means this is more power efficient when compared to what we have in OFDM. That means this requires more power to send and this requires less power to send.
Then why we not use SCFDM in downlink? Downloading, why we not use SCFDM?
See, whenever we are doing SCFDMA, our granularity will be somewhere around 180 kilohertz.
Then I want to ask what are the drawbacks of SCFDM?
See, SCFDMA, the drawback is whenever we are doing 180 kilohertz, our ISI will be more, isn't it? The intersymbol interference becomes high, and that to counter that again we have to cut it down into smaller frequency, isn't it? So we don't get that coherence bandwidth. So to get that coherence bandwidth, again we have to go for OFDM. You're getting my point? So you are asking what is the drawback of SCFDMA? To answer it, it is not going with a sort of coherence bandwidth of 15 kilohertz. we are grouping it into 180 kilohertz just for the simple reason that we want it power efficient to accommodate inside our UE. So that is why in typically SCFDMA is also called something called DFT spread OFDMA. It is actually same as OFDMA. Only thing is we are spreading our data using something called digital Fourier transforms and spreading it to 180 kilohertz. Okay, just to manage our power efficiency, we are doing it. See, if you look at it technically, it is same OFDMA only. Only difference is here we are spreading our data and making it so that it can be power efficient. Whereas here we need to have the smallest frequency, because if we don't do this, it will have an impact on IS.
One small question.
Yes.
In the downlink, we are using OFDMA. So when I'm transmitting from E node B to mobile, so when it is received in mobile has to understand the same this thing, right? So that time there won't be any problem, and mobile has to do the reverse.
Okay, see, basically the standard says how the frame is being designed for OFDMA, and this is already there inside your UE. So the UE already knows whenever a OFDMA data is coming to a mobile from E node B, what sort of 15 kilohertz I have, how the grouping has been done to 180 kilohertz, how this resource block allocation has been done in my frame, everything is predefined. So UE understands this. That means in OFDMA technique, transmitter is complex, but receiver is simple, because receiver has to just receive this data, right? Receive this data at this particular, let's say not 15 kilohertz, maybe around 180 kilohertz. So this is clearly sort of outlined to UE according to the standards or the specifications. Similarly, UE, whenever it is doing SCFDMA, it is doing at little lesser power, correct? But the receiver here will know at what power level it is and how to amplify this power. That is also taken care by E node.
Okay.
Okay. So to give you an analogy, let's say this is not an analogy which I should share, but still to make you understand. Let's say you go to a restaurant, you order a thali, right? And a person who prepares this thali has to do a lot of work, because he has to put lot of curries, the roti and the rice here. That is done by E node B, which is OFDMA. But the person who is eating this, that is UE, already knows that where the rice will be, where the roti will be, where the curries are being placed, where the, let's say, the dessert is there. So that means in OFDMA, which is taken care by E node B, the transmitter will be complex, but the receiver is very simple in OFDMA. The opposite is SCFDMA. In SCFDMA, the transmitter is simple. The receiver is complex. So both the complexity is given to E node B itself. The E node B can take that complexity because it has that enough bandwidth of the power or even the receiver sensitivity to take all this data. Okay. So just to make you understand, I have given you this analogy so that you can clearly understand what are the complexities which are there in OFDMA and SCFDMA. Okay. Yes.
In downlink, we grouping these frequencies in 12, right? And the source block is the 12 grouping.
Correct.
12.
Correct.
First thing, is there any specific reason we grouping in 12 only?
Okay, very good question. Yeah. Yes.
In uplink direction, do we have this grouping? Means like the source block?
No. In uplink direction, there is no grouping, because if I do grouping, again there will be something called PAPR, which will be high. So there is no grouping in uplink direction. Typically, it will be one single frequency. That's why it is called single frequency or single carrier. Okay. But there will be sub carrier itself, but that will be single carrier. In downlink, as you
means from in downlink we 180 kilohertz and uplink we 60 kilohertz.
Okay, see, they have mentioned here 60 kilohertz. Typically, it is 180 kilohertz. This is just generalized what they have mentioned. Typically, it will be in the order of 180 kilohertz. It might be one single 180 kilohertz or two 180 kilohertz. How we need to send this data is purely up to eNodeB scheduler. The scheduler has the right to tell a mobile which single carrier frequency a mobile has to upload. So mobile is not doing the single carrier on its own. It is all told by eNodeB itself. That means eNodeB has the authority to do the downlink as well as uplink scheduling. Okay. Is it clear? But always remember this will be in the order of 180 kilohertz only. It will not be 60 kilohertz. 60 kilohertz is an example what they have given just to show you about a comparison between this OFDMA and SCFDMA. But typically in LTE implementation, it will be 180 kilohertz. Okay. Now answer to you. I hope it's clear now.
I asked for the grouping region.
That grouping I tell you. So this part is clear, right? So the grouping part I'll come. It's an excellent question. Why we have come to 180 kilohertz is there is no technical reason. Basically, they wanted to get near to what we had with respect to 2G, which is 200 kilohertz. That's what standard says that we have got into grouping of 180 kilohertz. There is one more reason. I'll come to this. I don't want to jump into that because I'll just check whether am I getting that slide here. Okay, I'll just jump to this so that you will understand why it is 180 kilohertz. See, you remember this. I have concentrated at 20 megahertz, which has a subcarrier spacing across 15 kilohertz for everything. Okay, this doesn't change. Now, 15 kilohertz. Please remember, see, I am explaining why it is 180 kilohertz. I'll come. That's what I wanted to explain here. So that's why I'm jumping. So 15 kilohertz. How many 15 kilohertz are there in 20 megahertz? You can see here. How many are there?
Around 80.
Sorry, can you see here how many subcarriers are there in 20? You can see the number here. How much is it?
1200.
1200. So if you do 15 kilohertz, multiply with 1200, how much do you get?
Around 18,000.
1800.
Excellent. Very good. That means my actual bandwidth which is used for data is only 18 megahertz. That's why I didn't tell you that time. That means in 20 megahertz, always LTE standard says that 10% is always given as a guard period, because let's say this is 20 megahertz which is being used by Jio. The next adjacent 20 megahertz might be used by BSNL. So there should not be any adjacent channel interference. So to avoid it, LTE clearly specifies 1 megahertz on the upper side and 1 megahertz on the lower side. So totally 2 megahertz. Okay, 10% of 20 megahertz is how much? 2 megahertz. So 2 megahertz is given as a guard period. Actual data rate will go only in 18 megahertz. This is one of the reasons why they have cut it down into 15 into 12. 15 into 12, if you do, how much you get? 180 kilohertz. And 180 kilohertz, if you multiply it with 100, why? Because each 180 kilohertz, we call it as one resource block. To get this number of 100, they cut it down into 180 kilohertz, or they grouped it into 180 kilohertz.
But in FDD, that grid is not required.
Okay, see, remember this. Between 115 kilohertz and the next 15 kilohertz, I am not putting guard period. That's why it's called OFDMA, right? But if I consider a complete bandwidth of 20 megahertz, there is one more 20 megahertz which is there here. So if I don't give this guard of 1 megahertz, this will start spilling over here and it will create interference for the next channel. So this is called as adjacent channel interference. This was already there in 2G also. There the guard period was little less. Here we are giving a more guard period because we are going for higher bandwidth. So remember this, in 20 megahertz also we are giving 10% guard period only at the starting and ending. In between we are not giving any guard period. Okay. In between, whenever we are doing 15 kilohertz, here there is no guard period. The guard period or the guard band, we don't call it as period, sorry, it is guard band. It is 1 megahertz on the upper scale and 1 megahertz on the downward scale, so that it doesn't interfere with the next channel what we are giving. Okay. Similarly, 10 megahertz also has a guard period of 10%. That means only 9 megahertz will be used as the actual channel. The 500 kilohertz here and 500 kilohertz here will be used as something called as guard period. Okay. Is this point clear? Any doubts in this? Any doubts so far? Because even if it's silly or let's say you have any doubts, please come up, because this is kind of very important for you to understand to move forward with LTE, sort of, let's say, what I showed you about this table, right? So to understand this table, we need to understand this granularity. What do you mean by 15 kilohertz? How it is grouping done? As we got a very good question, why it is 180 kilohertz? So to understand this, we need to understand certain sort of concepts with respect to this guard band and let's say why we are giving that gap, right?
Dinesh, in this diagram, CP is general. What is this CP?
Where is it? Okay, CP. Okay, CP is cyclic prefix. Quick answer to this is, because again there is a cyclic prefix explanation being given. See, what is happening is, let's say this is my data. Whenever there is something called intersymbol interference, okay, intersymbol interference means typically if you speak in an echo channel environment, the last part will be more affected in the echo when compared to the first part of the data, right? So this is first part. The last part will always be having a lot of echo or ISI, intersymbol interference effect, when compared to the first part of the data. So what LTE standards specified was, since this is getting affected always when you are transmitting data, why can't I take this data and repeat here? So that even if I lose this data because of ISI, we can produce this data because already we are having a repetition of this data. This is called as cyclic prefix. Okay. More on this I will discuss whenever we are going to the frame duration. Okay. Is it clear now? What do you mean by cyclic prefix? Typically, we also call this technology as CPOFDMA or CPOFDM. So cyclic prefix is inevitable because we need to add cyclic prefix for our LTE OFDMA frame duration.
Vignesh?
Yes.
Yeah, this SCFDMA, it seems to be quite similar to TDD only. Only the frequency uplink and downlink are separate.
Okay, see, basically we cannot have a comparison with TDD. Is talking about the duplex technology between the user and the eNote, whereas SCFDMA is talking about a user's data rate upload, which is being done in a single frequency or at a single channel. That means in SCFDMA, maybe you are doing a comparison telling that, okay, we are talking in terms of one particular time slot, but here
and the frequency is same, right?
Correct.
Frequency is the single frequency. But what in TDD? But in TDD there is only one frequency uplink downlink, and here there is two frequency of uplink and downlink. Okay. See, for uplink it is only one frequency, and for downlink also separately one frequency. Right. So the division here is only on the basis of time.
Correct. And one more important factor you have to remember is what 180 kilohertz a UE needs to be transmitted in SCFDMA is purely decided by E node B. Whereas in TDD technology, it is already predefined by E node B. E node B doesn't explicitly has to mention this. So that's the difference between what you mentioned about TDD and SCFDMA. Okay. Okay. The next important factor is modulation. I think everyone are familiar with QPSK 16 QAM and 64 QAM, right? QPSK means, I'll just write it here so that you understand. QPSK means quadrature phase shift keying, wherein we have 2 bits representation, 4 combinations. So 0, 0, 0, 1, 1, 0 and 1, 1. Okay, sorry, 1, 1. Now, the next modulation scheme what we use is 16 QAM. 16 QAM is 16 combination, that is we require 4 bits. And if we consider 64 QAM, 64 QAM will have 6 bits to represent, okay, which is up to 64 combination. So please remember this, if I say 20 megahertz and if we are using QPSK modulation, okay, just to make you understand for a simpler purpose, very simple calculation is 20 multiplied by 2, this will be your actual throughput, that is 40 Mbps. Okay, if we consider the same 20 megahertz and implement 16 QAM modulation, then it will be 20 multiplied by 4 equals to, how much is it? 80 Mbps. Okay, and if we implement 64 QAM, it is 20 multiplied by 6, you get 120 Mbps. So this is how we are keeping our bandwidth constant and increasing the modulation scheme, which we call it as adaptive modulation. Now, why we call this as adaptive modulation? For the simple reason that our RF conditions are not equal throughout our cell coverage, right? So if you look at it here, let's say this is our E node B. Let's say this is the coverage area of E node B. Let's say the RF conditions are very good here. Let's say the RF conditions, I'll just take another color so that you understand. Let's say the RF conditions are very good here. Here we might implement 64 QAM. See, this is only for simplicity purpose I am putting the area wise. It purely depends on RF condition. RF condition might be signal strength, signal quality. There are more factors, right? Let's say this will be in a medium RF condition. Maybe we will go with 16 QAM. And let's say in the cell edge where the RF conditions are poor, we typically go with QPSK. Okay, so that's why the actual modulation scheme will not always be constant. Because of this, our data rate keeps on varying. Okay, there is a variation in our data rate. Even though the bandwidth remains same, the data rate purely depends on what modulation scheme you are in. Okay, is it clear? Now remember this, we are using three different modulation schemes which are adaptive in nature, purely depends on RF condition. You can see here, in good RF condition we go with 64 QAM. In, let's say, poor RF condition we go with QPSK. Okay, only one modulation scheme which is there, which is being not utilized by data transaction, it is used by a special channel here. I'll come to this channel on day 5, we are discussing this, which is called PH. So please remember this. This is the only modulation scheme which will be used for this particular channel. BPSK stands for binary phase shift keying, and PH is nothing but physical hybrid indicator channel. So what does this mean? I'll come to this whenever we are doing the channel mapping procedure. Okay. So same thing, constellation diagram they have shown here. If it is single bit, it is BPSK modulation, typically used for PH configuration. QPSK, 2 bits, 4 combinations. You can see here 4 combination. 16 QAM, you can see here 4 bits, 16 combination. And 64 QAM, what we have, 6 bits, 64 different combinations. Okay, so typically we call this as constellation diagram. So one more important factor we need to take care whenever we are calculating the data rate is nothing but the UE category. See, you can see here, UE category means if you have a UE category 1, your actual throughput will be only 10 Mbps and uplink will be 5 Mbps. Okay, it can decode 64 QAM
10 Mbps
and let's say if I consider, you can see here category wise, if I go with category 5.4, it will be typically 300 Mbps and 75 Mbps. So always remember this, only if I have E node B with let's say 20 megahertz and so many other features, the throughput also depends on what sort of mobile you have got. There might be some mobile, if I have a category 5, it will give a data rate of, or it can decode a data rate of 30 Mbps. Whereas if I carry only a category 1 mobile, it can decode only 10 Mbps at one particular second. So even though if a E node B wants to give you more data rate, UE can decode only 10 Mbps. So a throughput of LTE network also depends on what sort of handset we are carrying, right? And UE, E node B will also take into consideration about what sort of mobile you have got. So the moment you switch on your mobile, you need to send your IMEI details. IMEI stands for International Mobile Equipment Identity. Looking at this, it clearly understands what sort of category you have got, and based on this, a E node B will schedule a UE based on what data rate it can decode. Okay, so you can see here in the table, it starts with 10 Mbps, category 2 got little upgrade, 50 Mbps, 100, 150, goes up to 300. This is about release 8. Release 10 had more number of categories, about 6, 7 and 8, 3 more categories being added. And release 11, which is the next release of LTE Advanced, it goes up to 600 Mbps in downlink and 100 Mbps in uplink. Okay. Now, just to give you some understanding about this, CC means component carrier. This can decode only 120 megahertz, whereas this can decode 1 or 220 megahertz. This can decode 5 such 20 megahertz. Okay, so 5 means what? 5 into 20 becomes how much? This can decode 100 megahertz worth bandwidth. Okay, whereas these again will go up to 2 or 3. Right? So component carrier means how much bandwidth it can decode at one single time. So this can decode only 20 megahertz. So all release 8 mobiles can decode only maximum of 20 megahertz. Okay. And MIMO, I'll come to this. I'm not spoken about multiple input, multiple output antennas. So typically, whenever I'm explaining that, I'll come back forth and explain about what do you mean by 1 layer, 2 layer and 4 layer. So typically we have now 4 layers. So how it is being decoded, I'll come to that, and what do you mean by MIMO. Whenever we are discussing that, I will discuss about these layers as well. Any doubts in this? So I'll move forward. See, now you can see what are the different factors which will affect our throughput. We already looked at adaptive modulation. You can see here with 20 megahertz, if we have 64 QAM, it will be 120 Mbps as our speed. For simplicity, I am mentioning this. If we use same 20 megahertz and go with QPSK modulation, this will give a data rate of only 40 Mbps. So modulation will have an impact on your throughput in LTE. Coding. So if your coded bits means what? Let's say I have 120 Mbps as my actual data rate using 64 QAM modulation. Now always this data is not your actual traffic. Okay, it will also have some redundant bits. Why we add this redundant bits? Because in air interface, to put some security, we add these redundant bits. These redundant bits are called coded bits. Now, to give you an example, we use something called 1x2 channel coder, and also we use something called 3x4 channel coder. What do you mean by 1x2? For every one bit of our actual user data, we add one more bit as a code bit. So this is user data. This is coded bit. Coded bit means it is purely used for security, to secure in our air interface medium, because air interface is having a lot of issues with respect to, let's say, reflection, refraction, fading, and all these things. To counter, we do something called as coding. Now, if my actual throughput is 120 Mbps, in this only 60 Mbps will be user throughput. Rest 60 Mbps will be used for coding. So coding will also have an effect on your data rate. It's very important. Next thing is bandwidth. I think already we discussed this. From 2G 200 kilohertz, we have moved towards something called as 20 megahertz. In LTE, advanced, we have gone to 100 megahertz. In 5G, we have gone up to 400 megahertz. So you can see here clearly bandwidth plays a very vital role in increasing your data rate. MIMO, I'll come to this little later. Number of active users, as you already know, in our cellular network, if number of users start increasing, it will have an effect on your individual throughput as well. Scheduling algorithm, basically scheduling means that how many users get scheduled here, and based on that, it might, for one instance, this user might be scheduled. Another instance, this user might be scheduled. Based on this also, there will be impact on throughput. Distance between points, UE category, we already discussed this. Power, because sometimes we need to do a different power levels and it will have an impact on throughput. And access technology. As you can see, OFDMA has a better sort of spectral efficiency when compared to whatever we have in TDMA or even in CDMA. Okay, so spectral efficiency, just to give you an idea, how do you calculate spectral efficiency? It's very simple. Spectral efficiency means the unit is bits per second per hertz. That means how much data rate you are getting. Let's say if I get 120 Mbps using 64 QAM modulation, what is the given bandwidth? That is 20 megahertz. So it is like calculating the mileage of a vehicle, right? How do you calculate mileage of a vehicle? For a liter of petrol, how much kilometer it will give? Similar to that, the spectral efficiency here is with 20 megahertz, how much band data rate I am getting, let's say with 64.120 Mbps. So the spectral efficiency will be 6. So 6 bits per second per hertz will be spectral efficiency. If we go with let's say 16 QAM modulation, and the throughput will be how much? 20 to 4, 80 Mbps, and let's say 20 megahertz is constant, my spectral efficiency reduces it to 4. So this is how we calculate the spectral efficiency typically in any sort of technology. Maybe if you calculate in 3G, this will become 5 megahertz. That's the only difference. Okay. So now moving to the frequency domain configuration, I think already we touched upon this, right? You can see here 15 kilohertz is the smallest frequency what we have. Now in this, we already know that there are 6 different bandwidths. Right? Now we understand why we chose 20 megahertz, because we need a bigger bandwidth to satisfy our data, right? 15 kilohertz is also fine. Why? Because it is still a bigger bandwidth when compared to 3G. 10 megahertz is also fine because we have still more bigger bandwidth on 3G. Now 5 megahertz. Why we chose 5 megahertz? Because ultimately at one point of time we needed to tear down the 3G network and use that bandwidth for 4G. So that is the reason even we have a flexible bandwidth of 5 megahertz, which is being sort of defined in the specification. Now, till this is fine. What about these two? Why we require 1.4, which is as low as or lower than what we use in 3G, isn't it? Any sort of or any idea about why we have gone with 1.4 megahertz as the lowest frequency in 4G? Okay. Yes, please.
Handover required.
No, handover is being done in all the frequency bands, right? All the bandwidths, right?
This for maybe G, because
yes,
some subscriber have 2G set.
Okay, very good. Yes. So you are there up to that answer. Can you give me more substantive reason why it is 1.4? Okay. See, if you remember, the bandwidth for GSM was 200 kilohertz. And if you remember, yesterday I had discussed that to launch a network in 2G, an operator got 200 into 7 such frequencies. Okay, 200 into 7 such frequency to launch the network. Okay, to launch a network. So in 2G, to launch a network by an operator, they at least got allocated 7 such frequencies. So if you multiply 200 kilohertz into 7, how much do you get? 1.4 megahertz.
1.4.
That's the reason that if an operator who is there in 2G, if he wants to tear down his particular technology there and reform it using LTE, he can do it immediately by having this 1.4 megahertz. There are other reasons also. This typically might be used for something called machine type communication also, because machine type communication requires very low bandwidth. And this is also one more reason why we have gone with 3 megahertz, because LTE was not designed only for mobile broadband. It was also designed for machine type communication. It was also designed for let's say private networks. So all these things, considering these factors, they have put these two different bandwidths, which is lower than 3G, but it might play a very vital role when it comes to these kind of applications.
Okay. What do you mean by machine type communication?
Okay, see, machine type communication basically means that, let's say we have E node B here. Okay, typically we have a home, we usually call it a smart home nowadays. Let's say you have a CCTV camera here, okay, inside your home. You need to monitor this CCTV camera. Let's say you put a LTE chipset inside this, or let's say a LTE SIM card inside this. Now what it will do, a CCTV camera doesn't require a high data rate. It might want to just give you an update that, okay, who else had entered your house or who else is going outside your house. So to track this, what it is doing is it is constantly sending you a data, and we typically call it as machine type communication because this is automatically done. Nobody has to give any request.
Is it like IoT service?
Exactly. It is IoT only. IoT, another name for IoT is MTC. Okay. Or let's say you want to switch off your, or let's say you have a sensor in your home where you want to switch off your light, all these things. This is all machine type communication. This is all can be done by LTE network also. Nowadays, you don't see a lot of traction with MTC using LTE. It will be purely on Wi-Fi. You see Wi-Fi enabled bulbs, Wi-Fi enabled lights, all these things are possible. Wi-Fi enabled AC, Wi-Fi enabled fridge. All these things you are seeing more on Wi-Fi side, but on LTE side we are not seeing much traction. Even though standard specifies all these specifications on the IoT as well as machine type communication. So if you are clear with all these bandwidths what we have, only thing you remember this, 15 kilohertz remains constant. Only thing, the grouping of 180 kilohertz of 12, whatever we are doing, all this remain constant. Only difference is the grouping changes. Here it will be totally 900 subcarriers. Here it will be 600 subcarriers. So I hope you understood this particular part, right? If you have understood this particular part, you can make a relative sort of an analogy for this also. So here it will be 900, here it will be 600, here it will be 300, here it will be 180, and here it will be 72. See, extra they have added here one. It is a DC unit, so you can, if you minus it out, you get these numbers. And the resource block, what we get, as I mentioned about this, 1200 what we have is total subcarriers, but 180 into such 100 we get, that is 18 megahertz, right? So 180 is the one resource block, such 100 resource block we have got. Similar to that, in 15 megahertz we have 75 resource block, in 10 we have 50, in 5 we have 25, in 3 we have 15, and in 1.4 we have 6. I hope it's clear. There are no doubts in this. I don't want to get into this sampling frequency and FFT size because this requires a lot of complexity and a lot of mathematical calculation. So for the time being, I don't want to get into these aspects. Just digest these details because these details are very much important for us for our, maybe not for our daily usage, but it might be important for us to understand the technology per se. Okay. So this is very important to understand. This is very important to understand, and this is also very important to understand. Okay. And remember this, the frame, the subframe, I'll come to this, the subframe duration is 1 millisecond. Any doubts in this? So I'll move forward. Okay. Now let's come to frame details. Till now, we were looking at only in one dimension, that is frequency. Now we have to look at time also, because in LTE, it is not only on one particular domain, we also have to look at in another particular domain, that is time. Now, let's look at time. The first one is the frame duration. The frame duration of LTE is 10 millisecond. Okay. The 10 millisecond is actually divided into 1 millisecond subframe. You can see here in the earlier slide, as we mentioned here, the subframe. That means a frame of 10 millisecond is divided to 1 millisecond. That means we have totally 10 subframes. And remember this, this is very important. A UE gets scheduled in an LTE network based on this time, not on this time. It is not on 10 millisecond, it is based on 1 millisecond. A UE will get a message, a data or control information purely based on in the orders of 1 millisecond. Please remember this is very important. So 1 millisecond. So this is also called as TTI duration. You might have heard this in your literatures also. Sometimes TTI stands for transmit time interval. Okay, transmit time interval. So the subframe duration or TTI duration is one and the same. Don't get confused. It's one and the same. If I say subframe duration, if I say TTI duration or the UE allocation time, all are one and the same. It's 1 millisecond. Okay. Now this 1 millisecond is again divided into something called slot, and each slot duration is 0.5 millisecond. That means in one subframe we have 2 slots. Okay, so totally in one frame, see, in one frame we have 10 subframe, and each subframe has 2 slots. So totally we have 20 slots available in LTE. So you can see here 20 slots. Okay, 20 slots. Now these 20 slots, what we have, again this slot, there is one more granularity available. Each slot, you can see here time domain, each slot which is having a duration of 0.5 millisecond is having totally 7 OFDM symbols. So it starts from 0, 1, 2, 3, 4, 5, 6, 7. Sorry, 6. Sorry, it is only 6 because 0 to 6, totally it becomes 7. So there are 7 OFDM symbol in one slot, 7 OFDM symbol in one more slot. Totally we have 14 OFDM symbols. This is the smallest granularity in time domain. So don't get confused. The smallest granularity in frequency domain is 15 kilohertz. The smallest granularity, this is in frequency domain. The smallest granularity in time domain is 1 OFDM symbol. This is in time domain. So always remember this. Whenever we are talking in LTE, we have to talk in 2 dimensions. One is in frequency domain, another one is in time domain. So the time domain, we have the smallest unit is symbol. There are 14 symbols available in one particular subframe, or what we call it as TTI duration. Okay? Any doubts in this? Please ask, because this is quite important sort of concept what we have to learn with respect to the granularity with respect to frame as well as frequency.
Okay, what I understand from the frame, the total frame length is 10 microsecond.
10 millisecond. 10 millisecond.
Sorry, 10
not microsecond, 10 millisecond. Yes.
It's 10 microsecond. And there is 10 subframe.
Exactly.
Every subframe have 2 slots.
Very good.
Every slot have 7 times
FDM symbols.
FDM symbol, or it is time slot?
No, it is not called time slot. It's called symbol. Symbol means this. See, ultimately, this is called symbol. Such 7 symbols are there in one slot. In one slot.
One slot means 0.5 millisecond slot.
Correct.
Have 7 symbols.
Correct. 7 symbols.
One subframe have 2 slot means 14 symbols.
Correct. Exactly.
OFDM symbol.
Exactly. Very good. That's what it is. So now you have understand the time side. Now you understand the frequency side, right? One important concept here is to counter ISI. We have, as I discussed earlier, we have something called cyclic prefix. The cyclic prefix duration for CP1, cyclic prefix 1 till CP13. See, sorry, this has to be 13, not 3. CP13 is 4.7 microsecond, and cyclic prefix duration of only the CP0 is 5.2 microsecond. Now, why is this? I will leave it up to you. If you get the answer, you let me know. It's an assignment for you. You can let me know tomorrow also. There is no issues. If you know, you can let me know now also. We can discuss this. Or it's an assignment so that you can have a look at it.
Cycling prefix, right?
That's right. So cyclic.
Maybe there is a cycle of 5.2 microsecond. It will transmit, receive. It's for the maybe interference. There is some erroneous bit to correct it. So every 5.2 microsecond it will check or like that.
Okay, you're partly right, but this requires little bit of mathematical calculation. So I just wanted you to go through that. If you get some details on it, please come back, or else I will discuss this tomorrow again. Okay?
Okay.
So I don't want to get into these details because this requires little bit of mathematics, and I don't want at the end of the session to put it under some sort of trouble by putting all these mathematical calculations. So just remember this. In frequency domain, we have a granularity of 15 kilohertz, and 15 kilohertz is grouped into something called resource block by grouping 12. All these things are happening in frequency domain. Similarly, in time domain, the smallest granularity symbol, we are going to slot From slot we are going to subframe. From subframe we are going to frame. Okay. So why actually?
Just please go back.
Yeah. Please.
So in one subframe there is 14 numbers of 14 numbers of OFDM carrier.
Correct. OFDM
Symbol. Sorry.
Yes. So don't call it as carrier, because carrier is complete bandwidth of 20 megahertz. We are looking at a very small side. Okay.
Yeah. So then in one symbol, can I tell like that? In one symbol. This is one symbol for one user.
Okay, I'll come to that. I don't want to jump into that. The answer to that is, it is not one symbol for one user. Actually, this will be the user's actual allocation.
Sorry,
it is actually 1
your voice
millisecond.
is not clear. It is mute on.
Lot of disturbance. Person who is asking the doubt can mute it in
Please mute all after that. Rajiv Joy is talking.
Okay, fine. Please go ahead.
Okay, my because in one signal, one symbol,
right?
It is for one user.
No, not one symbol for one user. The user allocation will be this much. So you can say it is 14 OFDM symbols. A user will get at least 14 OFDM symbols. At least. That means it can be more than that. But minimum it has to get 14 OFDM symbols. Okay. It is not one single OFDM symbol. It is 14. Basically, we don't call it as 14. We call it as 1 millisecond, because this is having a duration of 1 millisecond, right? That's why I mentioned initially that the TTI duration or a UE allocation duration in LTE is 1 millisecond.
Okay, please correct this CP0 to CP13. This is 3. So when you upload, please correct it.
Okay, see, basically it is 13 only. You can see here, it is like this. That's all.
Okay. The one is
on the top. Okay, so please make sure that you understand this. That's why I told you about. Okay. Okay, now please observe this. Here we have put the complete grid of frequency and time. So you can see here on the frequency domain, this is 15 kilohertz. Okay, 15 kilohertz grouped into 12. Okay, grouped into 12 in one slot. See, you can see in one slot, this is 7 OFDM symbol. So now this single unit, what we have, which is 15 kilohertz into one OFDM symbol, this is called as 1RE. 1RE. RE stands for resource element. Okay. One resource element means you have to calculate in both the domains, frequency domain also, time domain also, both T. So 15 kilohertz in frequency domain into one OFDM symbol becomes 1RE. Okay. Now, how many such REs are available in one slot? How do you calculate? It's very simple. 12 into 7. So totally in one slot we have 84 REs, 84 resource elements. So if I ask you now, in one subframe, how many REs are there? So what is the answer?
168.
Excellent. So it's very simple. 0.5 millisecond has 84. Another 0.5 second will be 84. totally it will be 168 REs. So that becomes one resource block. Okay, this becomes one resource block. Here you can see this is called 1 RB, and there is one more 0.5 millisecond, there will be one more RB. So totally in one subframe, you have totally 168 REs, or we can also call it as 2 RBs, 2 resource blocks. Okay, this is, remember this is one resource block. There is one more resource block of 0.5. So in one subframe, you get total of 2 resources. So minimum a user, I think just now there was a question, how many allocation a user gets? A user gets minimum of 2 resource block in one TTI duration, or in one subframe, or in 1 millisecond. All are one and the same. So now you got how the resource allocation is been done in LTE. Okay, the last topic, I'll come to this. This is nothing but what do you call as reference signal. So why I've deliberately
Can you
put this.
please back over?
Yeah, please tell me.
Here, in left side resource block there is 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6, 7.
Okay, that's just for notation. See this one you're talking about?
Yes.
See, this is just for notation purpose, telling that all these frequency and time are divided to something called RBs, resource block. See, you can see here, this is one resource block. This resource block, they have again magnified and showed you that. You're getting my point?
Okay.
You're getting my point? This is resource block, they have again magnified and showed you that this contains 12 in frequency domain, 7 in OFDM, sorry, 7 in time domain. So totally it becomes 84. Okay. So I'll quickly move to this because this is sort of very important with respect to the calculation what we do with respect to the drive test or RF parameter. Typically we have something called as in our RF parameters, we have something called RSRP, RSRQ, all these parameters which are used to measure our channel estimation, what we do. So the channel estimation, whenever we do, this RS is nothing but the reference signal. Now reference signal is always used in our network to make people understand that what is the actual sort of power levels the E node B is acting upon. So here for reference signal, in our each slot, 4 REs are occupied by reference signal. Okay, so the reference signal is used for channel estimation. It is similar to in 3G we had something called C pitch. If people who are there from C pitch, 3G background might understand this. We had something called common pilot indicator channel, received signal code power. This was in 3G. Okay. Or in 2G we had something called BCCH channel. Okay, so this was used for channel estimation. Similarly in LTE, to do the channel estimation we require something called reference signal. This reference signal positions are already fixed according to the 3GPP specification itself. This you cannot change. Okay, according to 3GPP specs, in each slot the reference signal occupied will be 4, and these 4 placements, how it is done? In frequency domain, they should have a gap of 6 subcarriers. You can see here 6 subcarriers. In time domain, there should be a gap of 4 OFDM symbols. Okay. So this is how the reference signal has been designed, and this is purely used for channel estimation. This is used for channel estimation. Okay. So this is for, let's say, one antenna. Reference signal will be for one antenna. You might have seen that in our network typically there might be 4 antennas, right? 4 cross 4. Now I'll come to what this 4x4 means. Just remember this. If it is a single antenna, this will be occupied by single antenna transmission reference signal. But if you go for two antennas, the reference signal will also be different for the second antenna. You can see here R1. R1 is for second antenna. R0 will be for first antenna. So if you increase more antennas, for example, you can see here, this is there is a typo here. This is actually 4 antennas. If you go with 4 antennas, the number of reference signal will also increase, and this will have an impact on your throughput, because this is an overhead information. Okay, all these are overhead information, and because of this overhead information, these other slots can be used for your actual data, and this will impact your throughput. So how much throughput it will impact? If you have only one antenna, 4.76% of actual data will be taken care by reference signal. If it is 2 antenna, it will be 9.52, and if it is 4 antenna, it will be 14.29% of data rate will be occupied by reference signal. Okay, I have not spoken about normal and extended cyclic prefix. I will come to this tomorrow, because we need to discuss why there is a 5.2 microsecond in CP1 duration, and rest all will be 4.7. Whenever I am discussing this, I will talk about something called, there is something called normal cyclic prefix, extended cyclic prefix, and there is also something called as MPSFM cyclic prefix. Okay? So I'll come to all these things. Any doubts so far? So quickly summarizing whatever we discussed so far. As we discussed, LTE, which is also called EUTRAN, Evolved UMTS Terrestrial DoD Access Network, plus EPC becomes EPS, Evolved Packet System. LTE uses, as we discussed, OFDMA in downlink and SCFDMA in uplink. LTE uses an adaptive modulation, adaptive coding scheme. It uses QPSK 16 QAM and 64 QAM as modulation technique. The frame duration is 10 millisecond. Subframe of the TTI duration is 1 millisecond, and the slot duration is 0.5 millisecond. The TTI duration, this is very important. This is how user gets allocated, 1 millisecond. And the one resource block consists of 12 subcarriers in frequency domain, 7 OFDM symbols in time domain. So totally one resource block will have totally 84 resource elements, and one TTI will have totally 168 resource elements. Okay. So let me quickly go to the quiz, and then if any things are there in the chat window or any questions you have, you can ask me so that we can address those things as well. We have some 5 minutes of time. So minimum resource block a UE can get in one TTI is how much? 2. Excellent. It's 2. Because one TTI is 1 millisecond. 1 millisecond means 0.5 and 0.5. So 0.5, this is one resource block, and this is one more resource block. So minimum you will get 2. Maximum it can be how much? Anything. Minimum will be 2.
That can, in other words, can we say it is about 2 slots or 2 RBs?
Okay, you can say 2 slots. There is nothing wrong in saying 2 slots, yes. But yeah, because we will get 2 slots only. We will not get more than 2 slots in 1 millisecond. Yes. Yeah. We can say 2 slots, or basically we can say 2 RBs. Yes, it is correct. Okay. Okay, let me move to the next question. The total number of subcarriers in 10 megahertz. Is it 600?
900.
Excellent, 900. How do you remember this? It's very simple. Just remember the 20 megahertz. See, 1200 and 100. 100 resource blocks, 1200 subcarriers, right? Just reduce 300. So 900 will be for 15. It is actually 600 for 10. Okay. Just reduce 300 again. 300 is for 5 megahertz. Similarly, just reduce 25. So 75 megahertz is for 15 megahertz. For 10 megahertz, it is 50 resource blocks. And for 5 megahertz, it is 25 resource blocks. This is how we can remember. Okay. No need to remember it. You just remember the concept at least, so that it will be easier for you to understand all these things, right? The number of OFDM symbols in one subframe is
168.
no, not 4, not 168.
7.
14.
Not 7.
14.
14.
It is
It is
14.
14, not 7.
14.
Read the question here. It is one frame, not one slot.
Yes.
If it was one slot, the answer would have been 7 OFDM.
Then it is 7.
Yes.
It is
One subframe will be
actually
14 OFDM.
2 slots.
2 slots, correct. Excellent. Okay, next, the subframe or QTI duration in LTE. I think you can answer this.
1.
1.
1 millisecond. Okay, very good. Okay. Next, what are the bandwidths which are typically used in LTE? I think you can answer this also.
1.4,
Okay, 1.4,
5 up to 20
3,
megahertz.
5, 10, 15 and 20. Totally 6 bandwidths are available. Okay, totally 6 bandwidths are available. That's what is mentioned here.
Yeah.
Okay.
Yeah.
Fine. So I will end at this point. You have any doubts, we can just address those things now. I'll just look at the chat window. Okay, so just look at the chat window if any questions are there. Okay, answers are coming. Okay, there are no questions here. Any other doubts so that we can address, or we can end the session today? Okay, so thank you for patient listening. I'll meet you tomorrow at the same time, 4 p.m. Thank you, everyone.
Vignesh,